Thank you for giving this opportunity to present our work. And this work is a collaboration program between our company, Chasm Advanced Material, and the Center of Advanced Construction Material, CACM, from the University of Texas in Arlington. During this presentation, the title said a new scalable method for dispersion of carbon nanotube alumina hydride nanomaterial in concrete. This is not a conventional carbon nanotube. This belongs to the third category of in the historic evolution of the carbon nanomaterials. This material is more conductive and more efficient in performance than conventional carbon nanotube materials. Okay? And I will try to demonstrate during this presentation how our company has solved some barriers that do not allow the carbon nanotube technology to become a commercial reality in this particular application. Okay? Well, first of all, let me introduce our company. The mission of Chasm Advanced Material is to develop and manufacture advanced carbon nanomaterials to create a safer, more connected, and sustainable world. And we have two platforms of products. One, what we call the ENTEC, that is in the advanced carbon business. And in this ENTEC technology, we are developing and producing additives that are used for advanced concrete or construction materials, in this case, or additive for improving the performance of lithium-ion batteries. And the other platform that we call agent of printed electronic, we develop a material for transparent heaters and transparent antennas. Well, this is the current scenario of the cement industry. There are some difficulties and experience significant transformations. The difficulties is the pressure that are under this industry for the environmental concerns related to the production of a large quantity of CO2 during the production of the cement. This has motivated environmental or governmental agency to impose restricted regulation of the CO2 emissions in the atmosphere, and there is also an increasing growth in the market. And there are several solutions that are currently proposing by different universities, the academia, and the industry. But in our particular case, we are focused on developing alternative carbon nanomaterial that in combination with alternative material, we can partially replace cement. Okay, because carbon nanotube is an alternative nanomaterial for partially replace cement, this is due to their remarkable properties. It has been proven that carbon nanotube improves the mechanical properties of the concrete, enhance the durability, enhance the electrical conductivity and piezoelectric response, and also have high thermal conductivity. However, there are some issues associated with the use of carbon nanotube in this application. And one of the challenges is how to disperse in efficient manner these materials, because nanotubes tend to form bundles and ropes that when you try to disperse the material in the cement, they agglomerate, making difficult, less workable, and reduce the flowability properties. And there are some other issues concerning the cost of this material and the production at large scale. And there are some concerns related to the environmental and health impact of this material during its handling. And this is precisely the three main areas that we in Chasm are trying to address and to solve. Okay, because dispersion is one of the issues, there are at least two methods for dispersing nanotube in cement. One method is by blending mechanically powders of cement with the carbon nanomaterials, and the other is preparing a suspension of carbon nanotube. Okay. But why we need high dispersion? Because the dispersion has an important impact on the performance of the cement. And the dispersion method, to choose the appropriate dispersion, depends on several factors. For instance, the type of carbon nanotube and their morphology properties depend on also the properties of the cement material and also the specific application. But this is very important that I would like to highlight that the method for dispersing carbon nanotube must be both safe and commercially scalable. If this statement is not clear, we cannot get a commercial product. Okay, our company has the ability to develop and to produce different type of carbon nanotube material with different structure and different morphology. Our initial hypothesis during this project is how we can develop a material that is easy to disperse using conventional equipment. Well, we said, well, if we develop a material that is less entangled and lower structural defects, we can get a high possibility to disperse this material in cement using a minimum energy required for dispersing the material. And we create NTEC mesh morphology, as you can see in the slides, that has an aspect ratio between 200 and 700, and NTEC stand nanotube enhanced cement material. Okay, but we have also created another hybrid material that we call NTEC bundle morphology, that this material shows very high aspect ratio, and I will talk about this material during the presentation, how this material compare with NTEC mesh. Well, we prepare in the beginning of this project different NTEC mesh formulation having different carbon nanotube content in the hybrid material, and we blend with cement particles and different proportions between 0.10 to 0.20%. We chip this material to Chasm for determining the performance in electromechanical performance, and you can see an excellent performance versus mortar at different aging time. And then what is spectacular from this material is the high performance in the earlier stage. And there is some estimates that if the performance at the early stage is around 27%, we can arrive to potentially decrease the amount of cement in a proportion of between 25 to 30%. And you can observe after 28 curing time the increasing of performance of flexural properties. And that means that this material can be a good candidate for a mechanical strength. However, in the piezoelectric response, the results were lower than expected for the smart concrete application. In a smart concrete application, the level to be a good candidate has to get a response higher than 5% in piezoelectric response. Okay, how we can solve this problem? How we can increase the performance for piezoelectric response? Well, we developed NTEC B bundle. I showed pictures that this NTEC B bundle has higher aspect ratio. We synthesize this material that contains higher content of carbon nanotube in the hybrid material, in this case 60%, and you can observe the results after Kaken prepare suspensions of this material, different levels from 0.08 to 0.20, and only with 0.1% multi-wall on cement, we observe very positive results in performance versus mortar. The mesh, NTEC mesh, was better in compressive strength and also in flexural strength. However, we hit the goal with this NTEC bundle to achieve a level of piezoelectric response higher than 5%. We obtained 8.9%. That means this material can be suitable for applications related to smart concrete. We have been working for improving our method of integrating the material into the cement matrix, and recent results that we obtained using 0.2% of NTEC B bundle in Portland type 1, 2, and 72% of multi-wall nanotube in the hybrid material. We obtained a very high flexural strength, 85%, and very high compressive strength at 28 days of cooling time. There are some estimate that if we use the flexural properties is around 70%, we can reduce, potentially reduce about 25 to 30% the thickness of in the pavement. That means that we can use cover more surface area with the same amount of material, which has an impact on the cost. We can observe SEM images of the material as produced, and after incorporating or deposit these individual bundles of the cement particles. In this slide, I am comparing different manner to disperse nanotube in the cement, and you can observe the Kaken suspension method, the combination of Kaken suspension method plus the Chasm dispersion method. It's a multi-step method, and our improved method. What happened is when we combine both the Chasm suspension with the Kaken suspension with Chasm technology, we observe a very strong increase in flexural strength and also in modulus of elasticity. However, the compressive strengths remained lower in the level of 10%. However, the only method that is scalable at commercial scale is the improved Chasm mixing method. We have demonstrated the concept of blending the nanotube in powder form with cement particles using mesh morphology and bonded morphology, different cement coming from different geographical region. Some cement comes from Middle East, others from Europe, and others from the United States, and practically we observe the same performance profile. And as I discussed before, we have to provide a method that is effective and also safer for supplier to the customer. And we have two options. One option is integrate the method, install a reactor in the cement plant facilities and produce NTEC C and integrate the material during the process. And the other options will be granulate the material and then integrate the material in the cement plant, or with a ready mix or a precast producer company. And the last slide corresponds to how we solve the problem of supply, the amount of material required by the cement industry, low cost, and in a green process. Well, we have developed a green process because our technology, we don't produce CO2 during the process of manufacturing of the carbon nanomaterial. We recycle the unconverted ethylene. In this case, we have the ability to use different type of carbon source. And then we practically recycle the material, the gas, and we utilize 100% of the carbon atoms. And the hydrogen is separated, that the hydrogen can be used for heating the reactor or for using in other commercial applications. Our current capacity for producing in Tech C is 50 metric tons. I will show you how this is produced in our facilities. As you can see, a rotary reactor producing in continuous material. And we are currently designing and constructing a world's largest capacity carbon nanotube reactor that we expect to enter in operation by the fourth quarter of 2024. This capacity will be 1,500 metric tons of material, and the target price will be lower than $20 per kilogram. Okay, the conclusion of this work are in this slide. What I would like to say is we have addressed the main issues concerning how to move multi-wall carbon nanotube from R&D level to a commercial level. We have solved the main barriers by improving the method, developing a method that is scalable for dispersing the material, how the material can be handled in a safer manner and integrated in the material in an easier way, how produce this material in large quantities at an affordable price for the customer, and of course how this material shows high performance in the different areas of mechanical properties and electrical conductivity and piezoelectric properties. Thank you very much.